introduce vibrations, understand differential equations. We're going to review some of that, and then what we're going to do is Thursday program and code using MATLAB's built-in function to solve that. Okay. I think some of you have either taken DiffyQ or you're in DiffyQ, or maybe everyone's taken DiffyQ. I can't remember, but it's good review. Okay. Yes. Plus, we're going to get to Laplace, which is like proportional PID control for mechatronics students. And a lot of that is differential equations and solving differential equations. Okay. So having a good background on this is going to help. All right. So, but let's look at this. What the? Hornet wanted to learn some vibrations. It's weird. All right, so here we have, I'll zoom right in here, a spring on a mass, and we're going to look at this thing vibrating. And this could be on a table, but we're going to say it's frictionless, so no friction. Okay. So we have a spring, one spring, no damping. Okay. We have a mass that's on a frictionless surface, and we're going to pull this mass to the right, and we're going to let it go. Can someone tell me, in this case right here, what's going to happen? What would you see the mass do? There we go. So it's just going to keep going in the same motion with the same amplitude back and forth, right? And it's never going to stop because we assume no friction, there's no aerodynamic drag, and there's no damping, which we'll do next week. Okay. All right.
So the spring was great. Okay.
Eventually, it'll fatigue and crack. Yeah. Okay. But I can show you, we can model this. We can do Newton's second law. We can write the forces, which then generate a differential equation, and we can solve that. Okay. So the forces, the free body diagram, looks like this. If we pull the mass to the right, the spring force wants to push back to the left, right? Remember, spring force is Kx. Okay. Now, I'm also going to put on inertia term, the MA term. Okay. Do you know how Newton's second law is always the summation of forces equals MA? Well, I'm going to put that inertia term in, MA, in my free body diagram. I like to do that. Okay. So now all of my forces, they're going to equal 0. Okay. Now, why does it go to the left? It's because the mass is going to the right and it opposes motion. That's what inertia does. Okay. There's no friction forces. There's no other forces in the x direction. This is what we have. So if we sum the forces, in my case here, I'm setting them to 0 because I put the inertia term, the MA term, if you want to put this here, this is MA right here. So we get M, I'll put MA, plus Kx equals 0. We'll assume to the left is positive. This is mx double dot plus Kx equals 0. So, questions? Yes. Okay, that's what I was gonna get to next. But before that, any questions?
Well,
Good transition, Bob. Other than that question, you see what I did? You can take any free body diagram and you can create this equation right here, okay? Why did I put it, why do I have x double dot and x? Well, because x double dot is the second derivative. D squared x dt squared, right? What is this now? What did he just derive? What's it called? Second order differential equations. Most of you were in my intermediate fluids, right? We solved a few of those, right? Okay. So here's the thing. How, first off, what is a differential equation? What is it? You hear water drops right now. Okay. What is, like, why are they, why are they important? What do they do? Go back to this problem we did. What did I say? Like, if you looked at this mass system, what's going to happen? Wiggle back and forth. What does that wiggle mean? What are you looking at? Sure. Yep. Acceleration, velocity, and distance. X is distance. So it's solving for distance as a function of time. That's what a differential equation is. It solves a function. X is a function of time. Okay? Good. So we now know what a differential equation is. Where did it come from? Which is Newton's second law. Exactly. Okay? So you can derive a differential equation from Newton's second law. Okay? Any equation. Usually it's for motion, right? Where else have you seen differential equations? Have you ever seen anything else? Fluids. A lot of the times it's Newton's second law. Yep. Yeah, differential equations in class, sure. Circuits. Have you seen differential equations in circuits with current? Right? You have. Okay. So they probably forgot. I probably would forget too. Okay. But usually they come from some sort of set of equations. Okay. You doing okay on time? Yeah. So we know where one comes from. We know what they are. Now I have to solve it. Okay. Well, you have a whole class to solve it, right? I'm going to give you the solution here in a second. And I want you to tell me how that's the solution. Okay. But next class, we're going to program this one with an animation, so you can see this thing going back and forth, and it's oscillating up and down. Okay, with a subplot, so you can see exactly what's happening. Then we'll get into how you can use MATLAB and solve this completely without knowing the solution. Okay. In differential equations, how did you know, like, do you remember how you had to solve problems? Like, what are the initial steps of solving a differential equation? So look at it, and you have to classify it. Some of you already told me it's second order, right? Okay. What other thing can you tell me about this? M and K, they're constant. What? That's what second order is. Polynomial. So if you go back to the fitting homework, polynomial, this would be M of 2, right? Sort of. Okay.
Yeah.
Now, here, we know it's second order. M and K are constant. Do you remember the word constant coefficient? Did it ever ring a bell on differential equations? Okay. So anything in front of the derivative or x, if they're constant, then you can say it's constant coefficients. And what does it equal? Is it non-homogeneous or homogeneous?
It would be
50-50 chance.
non-homogeneous.
Homogeneous. Homogeneous. Okay? It'd be non-homogeneous if it was not equal to 0. Okay? We'll get to that next week because you got 2 solutions to that. You got a homogeneous solution and a particular solution. Okay? All right, cool. All right, I'm going to do something to this. This is just a formality thing. I'm going to divide by m. And I'm going to call this term omega n squared. So omega n squared, or omega n, is the square root of k over m. In vibrations, we do this. Anything in front of the double dot, we take whatever coefficient and we divide by that. Okay? And this becomes a non-dimensional or equation of state. That's what they call it. Okay? And it has omega n, which is the natural frequency. So if you have a beam, say you have a beam here, and it's mounted down here on a base or on a vise, and you hit it with a hammer, okay, so it vibrates back and forth. If you know the stiffness, you know the mass of that, you can figure out what its frequency is vibrating back and forth. That's its natural frequency. Okay. So that's why we do this in vibrations. All right. Don't worry too much if that's confusing, but that's just what we do. Now, there's a series of steps that you can solve this theoretically. And what you end up getting is this for a solution. X equals A sine parenthesis omega nt plus phi. How many would have taken this box equation and rearranged some stuff and solved for X? Okay, I have a lot of students do that. You can't do that with a differential equation. Okay, anytime you have a derivative or higher, the derivative is the power of 1, second order, third order, fourth order. Okay, you cannot just simply do algebra, right? This is a differential equation. You have to figure out how to do that. All right, so this is the solution. How? How can you check to see if it is the solution? And while you're doing that, I'm going to think about it. And can someone tell me what A and phi are? Whoops. And I'll zoom it back up, but I want to open something.
You're trying to show us that on the Teams, then it's not on Teams.
No, not right now. You can still see the X equation, right?
Yep.
Okay. So tell me how you can check to make sure that's the solution, and what are A and phi? Am I blowing some brain cells today? All right, I think this is what we're going to plot. Yep, perfect. Okay, so let's go back to here real quick. Let me zoom in. All right, well, this is the solution. The orange is the solution to this purple, right? So how do you check to make sure that it works? You've done it in differential equations. You just probably didn't realize what you were doing. Not the what? Derivative, right? Because this is x double dot.
Yeah.
Take the derivative twice,
Yeah.
put it in here,
Yeah.
plug x in here. What should it equal? 0. I would try that as practice for next class, just to make sure, okay? What is A and phi? Huh? Constants. Why is there 2 constants?
Because we don't hear the same.
Nope. Not K and M.
When you start taking the derivative things, you have to start adding in constants.
Yes. And how many, what's the order of the derivative? What, second order, right? So if you have a second order differential equation, you better have 2 constants. Okay? Cool. Now, A is found by this. And phi is tan to the minus 1 omega n x naught over v naught. Perfect. Okay. How the hell, sorry, pardon my French, but how is A and phi found? Not the derivative. So x at time of 0 is called x naught. V, which is x dot at time of 0, is v naught. What are those? What are those green things called? On the right, what are those things? What did I just do? Initial conditions. Yeah. So at time of 0, my initial position is 0, or some initial value, and the velocity is also some velocity, initial velocity, right? Why do I need 2 initial conditions? What's the order? Second order, you need 2, right? Okay. The other reason I like to help students with, let me move this, is if we're on a graph and we have x versus t, how do we know where we are initially? That's x naught, right? So, right here, this is x naught, right? Now, the second initial condition, the velocity, tells us what on a graph at the initial point. What's that? It's the speed. But you see how you have x dot, which is dx dt? What's that? Or on a graph, it's called a slope. Slope. The slope, well, it depends, right? It tells you the direction that you're going to go, right? That's why you need 2. You need the initial point, and you need the slope or the velocity to tell you which direction you're going to go, okay? So on the spring mass system, if I move it over a little bit and then let go with no initial velocity, it's going to go like this, okay? If I keep it here and then I kick it, some initial velocity, I'm going to go this way, okay? Whew. That make sense? So what we're gonna do, I'm gonna stop sharing here.